Hello, everyone, and thank you all for being here. I'm going to talk about my work with my advisor, Anshumali Srivastava. As the title suggests, we are going to look at a mighty effective and simple strategy to incorporate imitation in reinforcement learning and enhance exploration. So before going to that, let's look at what the fundamental problem of reinforcement learning is. So in reinforcement learning, we have an environment and an agent. An environment is basically a set of rules, and an agent is a player who abides by the rules and performs certain tasks. And the environment provides the agent with a state and a response in the form of a reward. So let's take the example of the classic Pac-Man game. A state can be as raw as an input image, as an image frame. And we have the agent, which tries to accumulate the dots while also dodging the enemies. Now, at this state, the agent can take 4 actions, up, right, down, and left. And each of these actions can lead to a different subsequent state. It will be a little more clearer now. Let's start with the state S0, and based on the action that the agent performs, you end up in a subsequent state and get either a positive reward or a termination or no reward. So you get different rewards and end up in different subsequent states. Now, for each of these states S1, based on actions, we can end up further in different subsequent states. Now, in reinforcement learning, what we want to learn is a neural network that takes the input as state 0 and tells us to take action up and end up in state S1. The same neural network has to take the S1 and also predict to take the action up again. So basically, we want to predict a trajectory that yields us good rewards while avoiding something like this or like this or like this. So just to contrast with supervised learning, in reinforcement learning, we have a state action pair as an input, and what we want to predict is a temporal reward. So we want a cumulative reward that sums up over the future. We want our future reward to be large. Now, in supervised learning, we just have an input-output pair that and we learn a function that maps the input to output. And we have a data set beforehand to start training. In reinforcement learning, we do not have a data set. So without a data set and without any training, we are basically playing random episodes. We are noticing random trajectories and learning the best ones from them, a typical case of genetic algorithm. What we want to do is we want to explore the good trajectories and avoid exploring the trajectories that lead to termination. So this is not easy. It's a big challenge, and even a celebrated AlphaGo 0 costs a lot. We saw Yu Wang talking about burning money. So this AlphaGo 0 is equivalent to burning money or melting glaciers, and it trains for 5 million episodes for more than 3 days, and it needs significant exploration to achieve superhuman performance. So what can we do to bring this cost down? One solution is imitation learning. So as the name suggests, in imitation learning, we are given a demonstrator or an expert, and what the and we have an agent that trains from scratch. We'll call it the novice. So as the novice trains, it has an option to query an expert. So I'm encountering this state. What is an appropriate action? So the expert suggests an appropriate action, and then the novice takes the action. In this process, it explores good sequences in the beginning of the training. And then it learns to map the state action correspondence of an expert. So just formalizing it, one of the prime algorithms in imitation learning is dataset aggregation, or Dagger. In Dagger, we basically use the expert's policy to generate state action pairs. So you encounter a state, you take expert's action, and you end up in next state, then take expert's action. In this way, we generate trajectories and add the state action pairs to a data set D. Now, if you look at this code snippet, the second line summarizes what Dagger does. Pi star corresponds to the expert's policy, and pi hat corresponds to the novice's policy. And in the beginning of the training, we rely solely on pi star, and as the training progresses, we reduce the reliance and finally cut it off. So this seems nice. We are generating expert trajectories and learning, but what are the shortcomings of Dagger? First thing, it is expected that we have experts policy as an oracle, but we do not really know how the expert was trained. Maybe we start with an architecture that can never learn the state action correspondence that an expert proposes. Second thing, the state space is really huge for most of the applications. So we need a lot of state action pairs to learn a function that directly maps and learns this correspondence of an expert. But we are asking a question like, okay, we do not have a state action correspondence and we do not have a lot of access to the expert. How do we solve this problem? Like, I cannot expect my advisor to give me, talk to me for 10 hours a day. With minimal interaction, how can I try to extract most of the information? So that's where we are trying to come up with we are trying to explore this aspect of natural tendency of mimicking by humans. Kids are fast learners, but for a large part of the time, they just mimic experts without really knowing the intricacies of why they are mimicking. But they become adept at using those strategies soon in their life. For example, when we learn tennis, the first things that we are taught to when we play forehand is to bend the knee and have a full swing, and then a follow through has to go to your shoulder. Without really knowing the state, we are agnostic to the state of where the ball is coming from, but then we are just trained to have this action sequence in our, inculcate this action sequence in our space, so that we explore its utility when we really come to the game. But inspired by this little thing, we are trying to blend observations and propose a hypothesis. That is, a novice has to be informed about frequent action sequences that an expert takes, and we just give the information about the action sequences and let novice figure out what to do with this through the usual learning process. So we don't change the algorithm, we just give the novice additional options to explore. So appending the novice's action space with frequent action sequences of the expert and training using any off-the-shelf reinforcement learning algorithm will improve exploration and leads to really better rewards and uncharted rewards. So now, how do we vindicate our hypothesis? So let's take this. Let's limit our sequences to just length of 2. So we're looking at action pairs, and let's have a toy example with just 2 basic actions. So a standard reinforcement learning would have a simple action space of as shown on the left side. What we are proposing is to append the action space with frequent action pairs. In this case, in this example, we are showing right-left and left-left to be frequent action pairs. Now, if our proposal conveniently beats standard reinforcement learning setup, we are good. Or maybe that's not enough, because what if we append all possible action pairs to the action space? Maybe it will do better. Or what if we just append a subset of a random subset of action pairs? Maybe that's going to still be better than the standard setup. So we need to explore whether the concept of adding frequent action pairs is doing something better or not. So we compare our proposal against 3 constructs of adding more information to the action space. So now let's look at some results on popular Atari games. We are going to show results for just 2 games, but one is Beam Rider and the other is Atlantis. The x-axis is the training time in hours, and the y-axis is the respective scores, respective rewards for the games. The first plot we are showing is basically the state-of-the-art GA3C algorithm, which from NVIDIA, and we trained it on V100 GPUs. So this is a standard action space. We are not messing the action space at this point. Now, the first thing is let's add all possible action pairs and see where it leads us to. So we expect adding all possible action pairs to actually enhance the rewards, but it's not consistent. For for one game it's worse and the other game it does something good. Now let's add a random subset of action pairs. It has the same behavior. It's not consistent across different games. Now, where does our proposed approach stand? It's like this. So we can see that there is a glaring gap between the baseline algorithms and the case where we append frequent action pairs to the action space. So although we show only 2 games, here we have we experiment with a lot more games, and each of this plot, each of this baseline is an average of 5 iterations. So definitely the trend is consistent across several games that appending frequent action pairs is doing something really good. So I'll summarize. We have 3 aspects. One is exploration in reinforcement learning is a challenge. And it can be solved by using imitation learning, but then imitation learning needs state action correspondence and a lot of information to get any reasonably close to the expert. And what we are proposing is to just append the action space of a novice training agent with expert action sequences and train from scratch with any off-the-shelf algorithm. And that leads to huge growth. So for more detailed experiments and insights into how do we get expert action sequences, we can refer to our paper on the web page. Also, we do have a fair bit of understanding of why this works, but theoretical formalism for this is really exciting, and if anyone is interested in that discussions, we will be happy to discuss. So thank you, and I can have some questions.
Questions for the speaker? Questions? Yes.
Does this sort of amount to like if you were training a neural network with supervised learning and then tuning it later with reinforcement learning?
I didn't.
Tuning. It sort of seems like a tuning.
That's how the typical dataset aggregation or other imitation learning frameworks work. In our case, we are adding the actions. We are giving the choice of having some action pairs, but we are not using any supervised learning. We are just letting it train from scratch by exploring itself. You just play the episode and learn. Play the episode and learn. We are not really giving any supervision in the beginning stage. That's how imitation learning works.
I'm just wondering, when you gave all the states action possible, it behaved worse than the frequent ones, right?
Yes.
So the performance was bad, or even the rewards, came out to be bad?
So we are plotting against time, and against time, the rewards have not improved. I mean, you train it further, probably it can catch up, but it's slower. Yeah.
Okay, we have time for one more question. Okay. So if not, we thank the speaker again.